Okay, welcome. This week I'm in Santa Barbara, California. It's pretty cold here, but I have a view out behind you of the ocean and the palm trees. So in case I do not look at you, it might be that the sunrise here is a bit distracting, but I do miss the snow that you have in Switzerland. So now we were stuck last week at how we optimize code, and the last point we got to was when you have the short loop of the fixed length, then it might be much faster to unroll the loop manually. Like here, that I write it unrolled for the scalar product x0 times y0 plus x1 times y1 plus x2 times y2, then to make a loop over the three entries, which does lots of checks, updates, and so on. So that is much slower than this. Sometimes the compiler can roll that by hand, and I've asked you to find out how your compiler manages that. The next thing is, if you have a loop that is long and that's of variable length like n, then we can't unroll the full loop. But if the n is large, it might be better to just do the 4 steps at once, like I plus 1, I plus 2, I plus 3, and then jump forward by 4, and then just do the last bit modulo 4 manually. This again can be done by the compiler if you find the right options. And again, you should try to see when the compiler does it. And here I wanted to ask you, how can you find out when the compiler does partial unrolling? Does anybody have an idea? Just pick up the microphone and push the button, and then they can see you and they can hear you. If nobody answers, then I want to talk to Jan. Jan, are you around?
No, I've disappeared.
You disappeared. So there's nobody here who has an idea?
Not yet.
How can you find out what the compiler is doing? Did you ever look at what the compiler does?
Look at the intermediate files, like the assembler code that is generated.
The assembly output, correct. That's perfect. You can look at that, and then you see what it might do, that it might just do multiple steps in it. Another way, you can just see whether the code gets faster. But the best is look at the assembly output. You don't have to understand the details, but you see when it does many more things suddenly, and does things 4 times. Or you look at the compiler manual, find the compiler options, and find options that let the compiler tell you what the compiler is doing with your loops. Now we can come to something important. I show you here 2 ways of doing a matrix addition. A loop over I and j, and I write A sub ij equal B sub ij plus C sub ij. Or in the second version, I write A sub ji equal B sub ji plus C sub ji. I'm telling you the first one is much faster than the second one. And why is that? To understand that, you have to think back to the cache exercise and to the hardware lecture, where we said that whenever you read a number into memory, the machine does not fetch just the number, but it fetches a full cache line. The cache line is of typical size of 64 bytes. So it fetches the first number and 4 to 8 further numbers. So when you read a number like here, the 00, then it reads in that value plus the next values as well. And if you then, in the next iteration, access the next value in the cache, then it's already loaded. And that's what we do here, because the J index grows up the fastest. So after the A00, the next value in memory is A01. So if the next one you read is A01, then it's fast, because that has already been fetched into the cache line, and that's in the cache. Well, if you switch the loops around, which seems a very innocuous change, then you next read the A10, and that's far away memory, and it takes just much longer. So the first loop here can be much faster than the second one. And you should always thus aim for unit stride. That means you should always try to access the next value in memory and not jump far. That makes the code much faster. And I talked to some the colleagues in the US, in Amherst. They had a code that was too slow, and they told them switch around 2 loops like this, and they were amazed that suddenly the code was 4 times faster. And they thought, I'm a genius. I told them, no, this is just what I'm teaching the second-year students. And it's the same for the matrix multiplications. Let's look at 3 loops here over I, J, and K. What if we make as the inner loop the loop over I? That's really bad, because then the A and the B gets accessed so that I make big jumps in memory. When I make the inner loop the K like I have here, then the B gets read in nicely, but for the C there's no unit stride. It jumps far in memory and it's slow. But if we put into the inner loop the J, then you see the CKJ gets access with unit stride, and so does the A for writing. And the BIK is even a constant and can be pulled out and stored into a temporary variable. But that's what the compiler will do for you anyway. So here, I'm just reading the C with unit stride, and I'm writing the A nicely streamed. And this is thus the fastest way of doing a simple matrix multiplication. But you can do it even better, because we know that if the matrix fits into the cache, then the matrix multiplication can be really fast. Why is that in particular important for matrix multiplication? The reason is, when we multiply matrices, then we have to read n squared data, because it's an n times n matrix. But then when we multiply the matrices, it takes time n cubed. So we have to do n cubed operations on n squared data. And I don't want to fetch the data n cubed times. That would be stupid. And so if the matrix fits into the cache, that is perfect, because then it's really fast and it can work really fast. But what if the matrix is too big to fit into the cache? Then things get much slower suddenly. But for matrix multiplication, you can still most of the time get close to the peak performance just by thinking of the following trick. If you take the matrix, like A, B, and C here, and if we split it into subblocks, I've sketched 9 blocks here, then you can multiply the matrix by multiplying those blocks. And if the blocks are small enough to fit into the cache, then it will be really fast. So to make things fast here, you should split the matrix into subblocks that are of the size that fits the cache, and then multiply those blocks at a time, and then the code will speed up enormously. And then on top of that, you can try if the Strassen algorithm helps you. And what we want you to do in the homeworks is to actually try to implement the matrix multiplication. A simple multiplication of big matrices. And we want you to compare it to the fastest existing library. And the goal for you is to get within a factor of 10 of the fastest library. If you manage to be not more than 10 times slower than a fast library, then you're good and then you've passed. If you get within a factor of 2 of the fastest library, then you get a prize from us. So try to write a fast matrix multiplication and try to beat the fastest library that exists. So that brings us to libraries. And first I want to talk to you about some the Fortran libraries, BLAS and LAPACK. And then later we'll talk about C++ libraries. But now the question is, can we use Fortran libraries from a C++ code? And many people say that you should use Fortran because there's so many fast libraries in Fortran. I then answer that's no reason to use Fortran because you can just call Fortran libraries from C++. But you have to know a few things, and you have to actually manage to do it once on your laptop and once on your workstation or your supercomputer. Once you find out how it's done, then it's very, very easy. If you don't know, you might be scared, and that's why in the homework we want you to actually call a Fortran function. And the first thing to remember is that Fortran, like C, does not mangle the types of the arguments with a name. So the name is basically just the name. And that's why you have to declare the function extern C. The next thing is you have to know how the Fortran function is called, actually. And if the function is called func, then it's typically written in uppercase in Fortran because in the old time there were only uppercase letters. And that function func is then usually translated into a lowercase symbol for the linker. So even if the function is documented with the uppercase letters, you should use the lowercase version. And on most compilers, you have to add an underscore. On some you don't. That's what you have to find out. So it's the function in the lowercase with sometimes the underscore appended. Then you can just call it. But then the question is, what do you have to link with it? You have to link with it the library. And then there's one other tricky thing that we have to practice once in the homeworks. And that is, you have to link it with the Fortran runtime libraries. Because when you compile a C++ program, then it links with it the standard C++ library. When you compile a Fortran program, then it automatically links your program to the standard Fortran library. Now the Fortran library we're using might call the standard Fortran library for I/O, but the C++ compiler links your code to the standard C++ library and not the standard Fortran library. And so you have to find out where the standard Fortran library is on your machine that you have to link with it. And the easiest way to find out is that you call the Fortran compiler, if you have one, and find out what libraries it links against, and then those libraries have to be linked to the program. We show you what you have to link on your laptops or on the workstation clusters of the physics department. And once you know how to link it, then you solved most problems. Because the rest is easy. The rest is just you have to know how the data types map. And the Fortran real is a float, and the Fortran double position type is a double. A Fortran integer is an int. But now there are two important things to remember, namely array indices in C start from 0. Array indices in Fortran by default start from 1. So if the documentation tells you that something is in the column 1 of a matrix, then you know it's in 0 in C or in C++. Then the trickier thing is the storage order of the matrices is reversed, so the matrices are transposed. I told you here when you add the matrices in C++, you have to make sure that the inner loop is the second index, because that's what goes up fastest. That's how matrices are stored in C++ and in C. In Fortran, it's the other way around. In Fortran, the I index goes up fastest. So that means that it's transposed, and when the documentation says that you should look at a row, then in C you have to look at the column. So it's transposed, and the index is offset by 1. Once you know that, then you can just call any Fortran library. Let's look at the BLAS library. The BLAS library is the library in Fortran for basic linear algebra functions, and there's one that is called d dot, which is the double position dot product. And when you look at the d dot function in Fortran, then it's declared this double position function d dot that takes an n, an x, an inc x, a y, and an inc y. And the x and y are the arrays of double precision, and the inc x and inc y and n are integers. And now, how do you declare the function before you call it? I told you you have to declare it extern C. It returns a double. The function is lowercase with an underscore. And now, how do we pass the arguments? Here you have to know that Fortran passes everything by reference, and never by value. And so for a scalar value like the n and the inc x and inc y, you just pass in a reference to an int n, a reference to an int inc x and inc y. And the arrays you can pass by pointer. So we have a double star x and double star y. So these are the only things you have to know, and then you can call any Fortran function that you want to call. So what is this BLAS library that I mentioned here? It's the basic linear algebra subroutines. It's an ancient, the Fortran libraries. It's one of the most successful libraries ever developed. And why is it successful? Because the people who developed it found a set of useful algorithms that many people want to use, and they defined a very nice high-level interface. Nice high-level for Fortran libraries. Since it's old, and it has 3 levels. BLAS level 1s are those functions that scale with the order n, so those which are linear. That's like vector additions, dot products, norms, and so on. BLAS level 2 are those that scale like n squared. That's a matrix vector multiplication, for example. BLAS level 3 are those which scale like n cubed, like a matrix operation. At first, it was just a Fortran library, and it can be found on netlib.org. Let us go there. Here we have netlib. When we look at netlib, then there are the libraries here, and I showed that last time. When you go into here, you find BLAS. Let me make it a bit bigger. Let's look at this BLAS library. and it shows you the basic linear algebra subprograms. It shows you what it is, and it has a table here of the sources. And you can look at various of these functions. And we can look for the d dot. Here's the d dot.f function, for example, that I showed before. It's a double precision function d dot. And then down here it implements the dot product in a bit optimized way. So it has a first version here that if the increments in the vectors are 1, so if it's just one value after the other, then it does some partial loop unrolling. You see here it does 5 iterations at once. If the increments are not 1, then it just does a trivial stupid loop. So it's a little bit optimized. But there are faster versions of it. So the key of the BLAS was not that this was a fast library. The key invention here was that somebody made a nice, flexible library that was useful, and that then other people wrote their codes based on the libraries, and the machine vendors provided faster version of the BLAS. Because if you had a code that uses the BLAS library, and you want to look for which machine should you buy next, if some vendor makes your code run really fast by having a fast BLAS library, then you might buy that vendor's machine. And so now we have the very fast BLAS libraries written by IBM and Intel and Cray and other companies. But what if you don't have access to such a vendor library? Then there's the Atlas library. What Atlas is, it's a library that optimizes a BLAS implementation for your machine. We learned, for example, that you can use Strassen. The Strassen is useful only for a big matrix. The question is, from which matrix size on is Strassen useful? I also told you that you should split the matrix into blocks, because the blocks fit into the cache, and if you do such a block matrix multiplication, then it can be much faster. But the question is, what should the block size be? And it really depends on your CPU, on your memory speed, on your cache, on your bus speed. So it's different from machine to machine. Now, the Fortran BLAS that I showed you is not optimized at all. On the supercomputers, the vendors hand optimize the code in assembly often for that machine, because they know it's really important, because they want to sell this very expensive machine. But nobody really optimizes the BLAS for every single laptop out there. And so that's where you can use Atlas. Atlas takes hours to compile. And why is that? Because it's self-tuning. When you build and compile it, then it tries out hundreds of versions. It tries out various block sizes and so on, and finds out what is the best block size for your machine, what is the best version for your laptop, and then once it found that, then it builds a BLAS library for you. So if you have access to the Intel the BLAS library, the MCAL, then use that. If you have a Mac, you get the BLAS library with the Mac OS. If you have a Linux machine, get the Atlas library today. Here is one old example from a book that I found. Here is the speed of a matrix multiplication on various matrix sizes from 100 times 100 up to 2000 times 2000. And the low line here, this is the Fortran reference BLAS. And it's pretty fast when it's in the cache, and then it gets very, very slow. When you look at the speed here and see, okay, that's 400 megaflop, then you see this was the old machine, but the qualitative features are still valid. Then on that machine, that was the HP1, HP wrote especially optimized the BLAS version that's 3 times faster. That's good. But still, once the matrix is not in the cache, things get slower. And now they have a faster one even. There's this one here. Now the speed is roughly constant no matter how big the matrix size is, because they split it into small blocks. And Atlas nearly reaches that speed. So it's pretty good. Because this one here is really handwritten, hand optimized. There have been 2 people, typically, or 3, spending a year on it in assembly. That's the second test, where one of the matrices is transposed that can be a bit faster. And there you see that sometimes even the Atlas wins out by a tiny bit. Of course, the Atlas does not win out for long, because in the next release of the vendor's library, typically it's again as fast or faster than Atlas. Who can tell me why? Why can Atlas never keep up with the vendor's library? Jan, do you know it?
Well, I guess the vendors can still look what Atlas does and do the same.
Exactly. Exactly. When you see that, you just do the same and it's faster. Very simple answer. So you should get a fast BLAS. But the BLAS can basically only do matrix additions, matrix multiplications, but we want to do the more, and for more there's the LAPACK library, which is the linear algebra package. And in the HPC course, we will then learn about the scalar pack, which is the parallel version of the LAPACK. That is functions for eigenvalues, eigenvectors, linear equations, matrix inversions, determinants, and so on. And it has functions for a general matrix, a symmetric matrix, a mission matrix, tridiagonal matrices, banded ones, and so on. So it's all the useful functions for dense matrices and linear algebra. And if you've used MATLAB or Python to solve an equation, then that program will have called the LAPACK library. Why is LAPACK fast? LAPACK is fast because to do the operation it calls a fast BLAS library that you have on your machine. So get the fast BLAS, the LAPACK will also be fast. Now those functions have a very cryptic naming convention that is easy to understand once you know it. And it's typically a 5 to 6 letter function name. And the first letter gives the precision. S is single precision, D is double precision. C is single precision complex, and Z is double precision complex. So the D dot function from the BLAS was the double precision dot product. Now for the LAPACK, the matrix could be a general matrix, or a symmetric matrix, or a Hermitian matrix, or a tridiagonal matrix, or a banded matrix. And the next 2 letters specify the matrix type. GE is general, SY symmetric, HE Hermitian. And the next 2 to 3 denote the operation. So, for example, this cryptic DGEEV function is a D for double precision, GE general matrix, and EV stands for eigenvalue solver. What would then be the single precision symmetric matrix eigenvalue solver? Would be S for single precision, SY symmetric, and EV for eigenvalue, so SSY EV. So the EV are the eigenvalue solvers, the SV is the linear solver, LS is the least square, and then you have some LQ and QL factorizations, matrix inverses, and so on. There are many useful functions in here. We'll use one of them in one of the exercises. What else do we need? We need to do the Fourier transforms, and there is a fast Fourier transform that most of you must have heard about. The question is, do you want to implement a fast Fourier transform? The answer is no, we don't, because we don't want to code. That's what I taught you. You should use the library. And for the Fourier transforms, there's the FFTW, which is the fastest Fourier transforming in the West. There's also a self-tuning library that tunes itself to your machine. And here we show it for, again, an HP machine. They wrote their first library, which was the one here. Then along came the FFTW. It was beating it at a big size of the vector. Then they hand optimized it and got faster again. That's this one here. So if you have the manpower and the time to sit down and optimize it for a machine, it gets faster. So if your machine has a Fourier transform library, then use that. If not, get the FFTW library. But this was linear function. It was the FFT, it was the linear algebra. What about optimization? Nonlinear ones. What about nonlinear root solvers? If I want to solve the nonlinear equation, interpolation, statistical functions, data analysis. This is much more useful, but that's where companies can make money. So these are not free. Those you have to write yourself or buy. There's the NAG library, for example, they cost money. If you work for a company, it's worth buying it. If you work for ETH, we have a site license. If you want to use it for your hobby at home, then it's probably too expensive. But you should know that they exist. And I want you to install a BLAS library, a LAPEC library, and a Fourier transform library for your laptops so that you have it for the rest of your studies. Now, we're coming to the next point. We're coming to how do you optimize C++ code. And what we discussed so far were things that you can use from C, from Fortran, from Python. So these are things that you can use in any language. What I teach you now are things that are just for C++. One thing we know is inlining. Next, I tell you about template meta programs, about lazy evaluations and about expression templates. Let me ask you, has anyone here in the class heard about expression templates? Jan, have you heard about it?
A bit.
A bit, yes. And the others? Nobody? Well, no. Okay, let's take it easy. What we're doing now is the most advanced part of C++, namely meta programming. And first, the question is, what is meta? And what is a meta program? And meta, if you look at the dictionary, means something that is one level higher. So for some concept X, the meta X is something about X. Like metaphysics is a discussion about physics and the world. And meta program in the program thus is a program that writes programs. So you can write a program that creates a program. That's a meta program. And you could now take a Python script that writes a C++ program. That would be a meta program, because a program that creates a program. But you don't need to write a Python script to write your program, because you can use the C++ compiler to write your program. What do I mean by that? Shouldn't you write your program? No, you can actually have the compiler create source code for you. And why it can do that is because the C++ compiler is a Turing machine. What that means is that the C++ compiler at compile time can perform any arbitrary computation. So anything that you can do on any classical computer can be done in a C++ compiler at compile time. That means if you want to do a matrix multiplication, the compiler can do it for you. If you want to check whether the number 15 is prime, the compiler can do it for you. If you want to write a program, you can write a program that lets the compiler write the program for you. It can check whether the number is prime. It can do loops at compile time. It can do if statements, it can do branches. You can do anything you could ever think of doing at runtime. You could also do at compile time. So any trick that you know of how to write optimized fast code, you can teach the compiler to do for you. And this is called meta programming. And here was the first example by Erwin Unruh in 1994. He wrote a template code in C++ that would print out error messages whenever a number was prime. So that way he showed that you can actually do loops and tests and all at compile time. Now, I don't think it's really important for us to write a program that prints prime numbers when you compile the program, but we can use it to make code fast. And let me show you why that is needed, and then I show you the first example, and then we make a break. So here is a dot product, and when you do the dot product and you do a loop here, then this might be fast for large n, especially if you partially unroll it. But for a small loop, that will be slow. Why is it slow? Because I set result to 0. So let's think of a loop of length 2. Then I set result to 0. I set I to 0. I check, is 0 less than 2? Yes. So I add A0 times B0 to result. Then I increase I to 1. I check, is 1 less than 2? Yes. So I add A1 times B1 to result. Then I increase I to 2. Then I check, is 2 less than 2? No, so I stop. So we do lots and lots So things just to multiply two numbers and to add them. And when you then look at the speed you get when you do many of those loops, then for the small vector length is pretty slow. For large one it gets faster. So for small vectors we want to optimize it. And if you have a code that works with many 3D vectors, for example, then you want it to be faster. So what you can do is you can write a specially unrolled function. So instead of having the n variable, I make an optimized code for a dot product of length 3. So an inline double dot 3 takes two pointers a and b, and it just returns a0 times b0 plus a1 times b1 plus a2 times b2. Okay, this is the perfect unrolled fast loop. It can be pipelined. It's just fast. But now we have to write a .3 function, we have to write a .2 function, a .1 function, a .4 function, a .5 function, a .6 function. And what do? We copy and paste. Should we do that? No. So you can never copy and paste, but we can use templates. So can we use templates to make such a dot function that is totally unrolled for any arbitrary n? This is yes, of course, because a C++ compiler is a Turing machine, so it can do anything that any classical computer can do, and that means it can write those functions for us. But how? That's what I want to show you now. So I want to unroll such a loop for any size n, but let me start by having a class called the tiny vector, which stores a vector of a fixed size n, and I template it on the type t and on the dimension of the vector n. In the class here I store the data privately in a fixed size array of length n, and I have a subscript operator that lets me access the data. But now I need to write the dot product. I want to write a dot product for two such tiny vectors of size n. So here is the dot product function. I write the function dot that takes two tiny vectors a and b, and they are templated on the type t and on the size n. And now how do we implement it? Here we use the fundamental theorem of software engineering. Any problem can be solved by introducing another level of indirection. We don't solve it here, we just delegate it. If I need to solve the problem, I just tell Jan, please do it for me. Right, Jan?
That's how it is.
Yeah, exactly. So you just delegate. So here the dot function doesn't know what to do, but it says I delegate it to some template. And that's this template class here, that metaprogram, this struct metadot. And we're calling a metadot of n-1 : f of a and b. So here is the metaprogram. Have a template int I, struct metadot. The I is in this case the n-1. And then in here I have the static function f that I'm calling, that takes two the tiny vectors of some length n. And what does it do? So how do I calculate the dot product of two vectors of length 3? So here's the trick. I'm calling this metadot with an index of 2. What is the metadot 2? What does it do? It does a2 times b2 plus the dot product of two vectors of length 2. So I just do it recursively. The dot product of two vectors of length 3 is the last elements multiplied plus the dot product of two vectors that are shorter. So I'm returning A sub I times B sub I plus meta dot of the index 1 less colon colon f of A and B. That passes in 2, then I go down to 1, then I go down to 0, then I go to -1, -2, -3, and it never ends. So we have to stop the recursion at some point. Because when we get to 0, when it's just the index 0, then we know it's special. When I get to 2 vectors and the length is 1, and I want to multiply the index 0, then it's just A0 times B0 plus nothing. So that's how I stop the recursion. What happens now when I call this? What happens in the compiler? I have, for example, here 2 tiny vectors of doubles of length 4, A and B, and I call dot of A comma B. That gets passed on to meta dot of 3 colon colon f of A and B. That is A3 times B3 plus meta dot 2, which is A2 times B2 plus meta dot 1, which is A1 times B1 plus meta dot 0, which is A0 times B0. All these many function calls can get inlined. When they're inlined, then it's just this totally unrolled expression, and that gets compiled. So what you get in the end is the optimal code here. It inlines it automatically. It might take a while to compile, but the code that you get is unrolled and optimal. And that's where we make a break now. Other questions? The answers to any questions I delegate to Jan. If Jan can't answer it, I'll help. Just talk to me, and we continue in 10 minutes otherwise. Okay, let's continue. So this was for fixed size vectors, but what if you want to do additions of long vectors? Let's write a simple class called simple vector, which is like our array class, and we write just the class. We write the constructor of a size, the copy constructor, the destruct, the assignment. We write the plus equal operation. We have the size function, the subscripts, and we store a point in the size. And now we add an operator plus. Here's template class T, simple vector of T operator plus. That takes 2 simple vectors, and we learned that that's very easy to do. We can just reuse the plus equal. So we copy x into result, call result plus equal y, and return the result. It's beautiful and easy, and then I can just write x plus y. But this code is not as fast as it can be. And here's the problem. If you write, for example, a equal b plus c plus d, what happens is, for the simple implementation of val array, or for the simple vector class, this gets evaluated as b plus c. And what happens when you do b plus c? When you do b plus c, let's look back at it. We create a new temporary variable result, which we then copy back. So what happens is b plus c gets copied into a new temporary temp1. To that I'm adding the d. That gets stored into another temporary 2, and that then gets copied into a. That means I'm copying 3 times. I need 2 temporary vectors, and I'm copying it. So to see what it does, let's look at a first example and look at the timings. and have it here. Let's see. Here I have the code. If we go to the week 12 directory, we have this simple vector class here. I have the constructor, I have a swap, I have an assignment, I have a plus equal, and we have this operator plus. And then we have a program to time it. Time simple.cpp. Here we take a vector, and what's the size that we should take? Here we took a size of 1,000,000. We take 3 vectors of that size 1,000,000. We make a loop where 1,000 times we add those vectors. And now I'm going to build it. I go into this build directory. I make cmake on it, and let's look at the options. I want to build it in release mode, that it gets optimized, and I have to make sure that, okay, when I do release, I actually want to do, let's use -03 and -d and debug. That is nicely, strongly optimized. Now let's make these programs, and I can run the time simple program, or I can time it. And it takes about 4 seconds. Let me run it again, because it's not always the same speed, so it was, yeah, but it's about 3.94 seconds. And we have the other version, the time simple 2. That takes just 2 vectors that it adds, and that takes about 2 seconds. Let's look at the time simple 2.cpp program. That's the same, and it takes 2 vectors. Let's see if much changes if we make the vectors longer. Let's make the vectors 10 times longer, but let's do it only 100 times. Yeah, that makes it longer because I've copied more. So let's do that. 3.2 seconds. And the time simple.cpp, let's also make the vectors longer. Each you have to make it longer because the cache sizes increase. When I'm timing this time simple, it also takes a bit longer now. It takes about 6 seconds. Okay. Now we want to make it faster, because this is slow because things got added here and copied around. So what I now want to do is a very important concept of lazy evaluation. If I do b plus c, what we did before is that when I added 2 vectors, it actually did it. When we looked at this simple vector again here, the operator plus of 2 vectors actually adds the vectors and writes it into a temporary object. But we want to avoid doing that. How can we avoid doing that? We can avoid doing that by simply not adding it. What we can do instead is we can be lazy, and what I can say, what is the sum of A and B? You can simply tell me, hey, it's easy, it's the sum of A and B. I don't have to tell you it's this vector here, but I can just tell you it's the sum of A and B. So that's exactly what we're going to do. We're going to have the operator plus of 2 lazy vectors, not return a new lazy vector, but just return a vector sum object, something that says, hey, I'm the sum of x and y. So here's this vector sum object on the left, the class. What I'm going to store is, I'm just going to store 2 reference. I'm going to store the reference to the left-hand side vector and the one to the right-hand side vector. The constructor takes those two and it just stores the references, so it's super cheap. But what I need is when I want to say, okay, yes, I know you're the sum of B and C, but what is your second element? Then at that time you do it. So when I do the element access, then only I'm going to add it. So I'm lazy. I'm not doing the addition when you ask me to add it. I'm going to do the addition only when you ask me to evaluate the addition at a certain index. So the operator plus just returns the vector sum object, and then only when I assign into it. So here I'm assigning a vector sum object into a lazy vector. Here I make a loop. And at that time, I'm doing the loop and I'm evaluating this vector sum at the index I. So this gives you the optimal code because now it's only a single loop when I write the A equal B plus C. The plus just gives me this proxy object, the vector sum that tells me I'm the sum. And then when I assign it, then I'm doing the single loop and I get the optimal fast code. And that's what we're going to look at now, what the code does. And that's what's always interesting, because from year to year the machines change and the compilers change, so one never knows what comes out. So let's look at this lazy vector. So the HPP, it's basically the same as before, except that we have this vector sum object that I showed you, and the operator plus returns the vector sum. And now I have also a time lazy vector. Time lazy 2.cpp. And we have to make the same change in the sizes. I'm going to compile it. And now I'm going to run it. And it takes 0.0005 seconds. What was the time simple? 3 seconds. So we're now 1,000 times faster. As I told you, every year there's a surprise. Fortunately, I checked it this morning, so I know what's the surprise. But who of you can tell me what's going on here? Why is this 1,000 times faster? I typically expected a factor of 2 faster, now it's 1,000 times faster. Wow. Can make the vectors even longer. We can make now 1,000,000 iterations. I think it will still be 5 milliseconds. What's going on with this code? Why does this code only need 5 milliseconds?
Because we actually don't do anything?
Probably, yes, we don't do anything. The compiler managed to optimize it out completely. And why that? Because the compiler, after I wrote it, realized, actually, I don't need B and C. I don't need A, I don't do much with it. The compiler managed to totally optimize away all of the code because I'm not doing anything. Now, what can we do to avoid that? That's the first big lesson to learn. Make sure when you do benchmarks that the compiler doesn't optimize away your complete program. What can you do to avoid that? We have to do something that makes the compiler actually think that I need the result. So you can do something like, okay, let's try something. Does anybody have a suggestion? Jan, do you have an idea?
It's always good to write the result out.
Yeah, it's always good to write the result. So let's do something like, let's try. Let's write A sub 0. Let's do something like this. Okay, that was the time simple again. As a check, it's about 3 seconds. Now let's try the time lazy 2. Okay, it's no longer 5 milliseconds. Phew, we managed. It's now 1.8 seconds. We're faster. Good, so lesson number 1, make sure that you don't optimize away the code you're actually timing. Lesson number 2, when you optimize, your things get faster. But this was pretty easy here. But there are 2 restrictions. First, it only works for plus operations. Second, it only works for 2 vectors. What should I do if I also want to subtract vectors or multiply vectors? I could write a vector difference, a vector product, a vector quotient, a vector modulo, and so on. I can write a new class for every single operation. And they all will look very similar to the vector sum. The only difference will be the vector difference has a minus in here. The vector product will have a star in here. The vector modulo will have a percentage in here. So the only thing I'm changing is the operation here, and the rest I'm just doing copy and paste. But that's a big no, right? I told you never copy and paste. So what we're going to use instead is we're going to template it on the operation. So what I'm going to do is I'm going to do this vector sum object, but the one thing that differs from addition to subtraction, multiplication, and so on is just the operation I'm using in the subscript operator. And that's what I'm going to do now is I'm going to template the vector sum also on the operation. And I should call it vector op probably instead of vector sum. But let's just add this extra template parameter here, the operation. And then let's assume that it has a function apply, and that's what I'm going to call here. So I'm calling op apply of the left and the right hand side at the index I. And this op can, for example, be a plus. So I'm going to define a plus class here. And the plus class has a static inline function apply of 2 values that returns the sum. We're going to have a minus struct, and the minus has an apply function that does a minus b. We can have the multiplies function, and you've guessed it, the multiplies function has an apply function that returns a times b, and so on. And then we have the operator plus. And the operator plus now simply returns a vector sum of t comma plus of x and y. And we have the operator minus that returns the vector sum of t comma minus of x and y. And the assignment we also just have to template also on the operand. That we call the lazy vector flex. So the lazy vector flex now does the same things, but I can do a plus b or a minus b. Let's time it to see whether that has cost us anything. Time. So let's open the time lazy flex. Do I have that? 2.cpp. We change the sizes. And we have to remember to actually, this here compilers have gotten good enough that they realize that we're not doing anything. So let me print out something to fool this year's compiler. Because if the compiler were smart, it should know that this has to be 0 and it can just print 0. But this year's compilers is not smart enough. Time lazy flex, that's with a subtraction. Shouldn't run the CVP file, but the executable is again 1.8 seconds. 1.823, 1.821, 1.849. Okay, you see, I worried a bit because before it was 1.832 and it suddenly got faster. But when I run it a third time, then it gets slower. So that's the measurement noise here. It's about 1%. Good. So now we have the program that we can also subtract vectors. But still, I want to do more. Because I want to do things like b plus c plus d, or b times c plus d plus x power of e, or b minus c plus a times b. How can I do it for general expressions? Do I have to write a 3-vector sum, or a vector product, or a product of 2 vectors times a sum, or a sum of 2 vectors times a sum of 2 vectors? Do I need to make an expression class for every single expression? The answer is no, because I can make the compiler do it. And we just have to make templates of expressions. And this is one of the most advanced C++ tricks, so I want to go a bit slow here. What I want to do here is I want to make a general expression class that I can recursively use. And the way I'm going to do it is a very tiny change to the vector sum class, but it will have a huge impact. When we looked at this lazy vector sum, that takes 2 vectors and the operation, and they store the reference to the left-hand side vector and the reference to the right-hand side vectors. I'm now going to generalize it by saying this need not be a sum of 2 vectors, but it can be a sum of 2 anythings. So I'm going to template it, this expression class x. I'm going to template it on the thing on the left, and the operation, and the thing on the right. So it's template class L, class operation class R. In the constructor, I'm passing in the thing on the left, the thing on the right. In the class itself, I'm storing references to the thing on the left and the thing on the right. And when I evaluate it, I apply the operation to the thing on the left evaluated at the index and the thing on the right evaluated at the index. It's just a little bit more general. It's no longer a lazy vector, but it can be anything. And anything means including any complicated expression. Okay? This is just an object that stores a reference to the stuff on the left, stuff on the right, and it has the operation. And now I can write something like here. We had the lazy vector. The sum of 2 lazy vectors was this vector sum object. This I'm now going to replace by my operator plus for the expression template vector, the ET vector. For this, I'm going to add an operator plus for anything on the left plus a vector. The thing on the left could be a sum of 2 vectors, a sum of 3 vectors, could be a product of vectors. So anything plus a vector gives me, returns, an expression object of whatever the thing on the left is, plus the vector. And then I need the assignment. In the assignment, I could assign a vector sum into my lazy vector. I'm going to change that for the expression template vector. I can assign any expression into the vector. And the way I do it is I make a loop up to the size. I'm going to evaluate the expression at the index. I'm going to assign it into the vector. And that's all. This might seem like magic, but this now can do the d equal a plus b plus c. And let's see what the compiler does when it encounters this expression, that the vector d is a vector a plus b plus c. It first looks at a plus b. For a plus b, it's going to use this operator plus that we had. In this case, these are 2 vectors, so the L is an ET vector. So this will return an expression object for vector plus vector. And this we call the constructor here, of vector plus vector, initialized with a and b. And then what's left is, this has to be added to C. So it's this plus C. Now again, the same template is used, but now on the left-hand side, I have this expression. The operator is plus, and on the right-hand side, I have the vector. So this will now call a constructor for an expression object of a vector plus a vector expression plus a vector. You see, we have a recursive structure for the type that captures the expression. And now I have constructed a type at compile time that captures the structure of the expression, namely it's a vector plus a vector plus a vector. And then I assign it into D, and that assignment into D calls this assignment operator, and I just do the loop. And now at every index I'm going to evaluate this object here at the index I. What happens? It calls plus apply of the expression on the left at I and C of I, which is the plus apply of A sub I and B sub I plus C sub I, which again gets inlined to A sub I plus B sub I plus C sub I. So it gets aggressively inlined, and at the end, this loop is just P sub I equal A sub I plus B sub I plus C sub I. It's the loop that you would have written by hand. After that, the compiler realizes it doesn't need those expression objects. So the code to create the expression objects gets removed from the code, gets optimized away, and you're left just with this optimized sum that you would have written by hand, but you didn't have to write it by hand, you could write it at the high level. And let's see if this actually works. So let me look at the expression template, timet.cpp, and we're going to change the vector length again, and do the A equal B plus C plus D here. And let me again time the simple. Time simple. That was 6 seconds. Now we're going to time the expression template's version is 5 milliseconds. What happened? We forgot to realize that the machines today are so fast that they realize that that they don't even do the additions because they realize that we don't need the value. So let's fool it by printing the result, A sub 0, and building it again and timing it again. And it's 2.4 seconds instead of 6.4 seconds. It's quite a bit faster. So it works. It's faster and flexible. And I can now go in there and I can do more changes. I can time ET CPU. I can do some subtraction. I can add other vectors. I can do parentheses and whatever. I can compile it. No, we didn't have. We still have to implement the operator minus. So I forgot to add that. This homework for you. Now, how do you think can anyone come up with such a great idea as these expression templates? Was that the famous professor who invented that? Was that a postdoc? Was it a PhD student? Or how old was the person who invented those expression templates? What's your guess? Jan, can you get somebody to make a guess? So can you check around? how old you have to be to invent such a thing?
"42 years."
3 years. Another guess.
$16.
16. It's a bit more than 16 is 20. It was a bachelor student in Waterloo. So the bachelor students, like, you can invent such tricks. And then he showed that, and then he wrote the library as the bachelor thesis, the Blitz library, that had both the tiny vector and the expression templates. And on that old machine there, okay, that was the very old one, you see, because that ran at about 60 megaflop a second. But on that one, the C++ val array was very, very slow. You see, for a small vector, it had maybe 1 megaflop. For a large vector, it reached about 20 megaflop. If you wrote it in Fortran, for the small vector, you reach 50 megaflop. For the big vectors, you reach about 60. The tiny vector with the unrolling that you wrote reached 65 megaflop. And the expression template vector class that you wrote reached the same performance as the Fortran code. Why does it drop here? Why does it drop when you add vectors? Why does it suddenly drop at a certain vector size? Any answer?
Yeah, because it's out of the cache.
It's out of the cache. Yes, we had that in the cache exercise, right? Beautiful. Know that now. There are libraries now that use that. There was the Blitz library that the student wrote. That was one of the first expression template of the libraries and more. And I want to show you some of those libraries now. The first is the Blitz library. That was the web page. It is here no longer maintained, but you find it in the Wayback Archive. That did a tiny vector class and then the array class. He invented a few more nice tricks. Like, what if I want to calculate something with 3 rays? Vector that comes in, gets reflected off a mirror, and goes out. So I want to implement this expression here. He wrote the tiny vector class. And then he set it, and he did here something like n equals 0, 0, 1 to set the normal vector. Is that legal syntax? Can you implement that? Probably yes, because they show it. But how can you implement something like this? The vector n equals 0, 0, 1. Or is that an April Fool's joke and that's not legal? Any answer? Jan, can you help? Other people around have an answer? Who thinks it's an April Fool's joke? That they're fooling you?
No one's having his hands up.
Then somebody should tell me how that can be done.
Any ideas?
Now let's look carefully at what happens here, right? I have 0, 0. What is being done? No, so I have, so the first is n equals 0. So I'm initializing a tiny vector with 0. What's the return value of the assignment? It's typically a reference to a vector, right? And then, if I pass the syntax, what comes next? Comma. What is comma? Comma is an operator. I can implement an operator comma. And that is being called. So this is operator overloading on the comma operator. And that's the trick that is being used. That this assignment of 0 into a vector gives me some object for which then the comma operator is overloaded so that I can write 0, 0, 1. It's a beautiful trick that he found. And then he does here a sum of I times n, that's the dot product times n, and he gave a beautiful fast code. Then he invented things for array expressions, right? We had this a plus b, a minus c. He added exponential functions, log functions, sum functions, so that when you want to calculate the free energy of some system, which is the equation here, you just write it like the equation, minus t times log of sum of minus exponential of, okay, no, there should be exponential of minus energy divided by t. And it just works, it's easy. And the benchmarks, I showed you it was fast. Then you want to implement some partial differential equation, like a diffusion equation. And so we need to implement a second derivative. We iterate, and then in every time step, the new temperature at some index I is the old temperature plus a constant times the value on one mesh point to the left, I minus 1, plus the value at one mesh point to the right, I plus 1, minus twice the value in the center, and I have the loop here and then a swap. Now, what's not nice here is that I have to make this ugly loop where I access every single array element. What Todd Feldhuisen, the author of the bits library and the inventor of the expression templates, found out is he realized we can invent a range object. So he invented the concept of a range object of something that tells me do that operation for every index I from 1 to n minus 2. So there's the range object. And now I write the same equation, but as the index, I don't pass an integer, but I pass a range object I. And I have the range object I here and I here, I minus 1 here, I plus 1 here, and again I there. And when you compile that, the compiler expands that automatically into a loop for you. So you don't have to write the loop, you just specify the range object, and you get the library that does it for you. So this just shows you how high level you can program in C++, and the code can still be fast because you can still make the compiler turn that into optimal low-level code. But then that's still not nice because we had to write this old temperature on 1 to the left, plus 1 to the right, minus twice in the middle, and and we have to write that whenever we do a second derivative. When you go to 2 dimensions, then it's 1 point to the left, 1 to the right, 1 up, 1 down, minus 4 times the middle. In 3 dimensions, is more points even. But this is very, very common. Whenever you do a finite difference solution to any PDE, you need that. So you can make a so-called stencil. You can make an object that captures that. And then you can just do something like a Laplacian 2D. You can say just apply the 2D Laplacian operator to that array, and it does it. And now that's the 2D version. The 3D version is simple as well. So you can write it even higher level and still make the code fast. And that again was invented by the same bachelor student. And here's some the old benchmark of using that for some 3D wave equation, where the Blitz code used about 200 seconds with 9 lines of code. The Fortran code in the Fortran 90 was quite a bit slower, in Fortran 77 slightly faster. Then one could tune the Blitz code by removing the swap calls. The Blitz code went down to 8 lines of code and was faster. The Fortran codes are much longer and about the same speed. Then people thought, okay, that's nice, but we want to make it parallel, and we don't want only arrays, we also want particle methods. And they said, okay, let's write the library that does particle codes and mesh codes, that does it beautifully high level with expression templates and stencils, and that automatically parallelizes the code. So that you write the code at that high level and you run it and it's automatically parallel. Now that was a great project that was started at the Los Alamos labs. The people started doing that, they became famous, companies brought them up, and the project died. So when you invent such a great library or tool, and you know how to do it, then you're in this big demand, then you earn $500,000 Swiss francs or more easily, because people want you. So those are things that you should learn and that are worthwhile to learn. What can you do with the Puma code? You can basically make such a code and make it parallel. And this is the same code, now a bit more complex, but with Puma, it does a 2D heat equation in parallel on a supercomputer. I've had one student who started a thesis doing a work on simulating X-ray lasers, and he found that a bit hard, and he said, can I really do that alone, a parallel program? And I told him, it's no problem, just use Puma, that should be able to solve it. So he tried it, he downloaded it, he tried to compile it, there were some bugs that he fixed, and after 2 years, he had a code that worked. And he thought, okay, that was very slow, it took him 2 years. Then he wanted to go to a conference to show that code he did, and he sent an abstract for a poster. They wrote back that they want him to give a talk there. He gave the talk there, and after that somebody from the Stanford Linear Accelerator Center came to him and asked him, when do you finish your thesis? Because we have a job for you. What you've done in 2 years with Puma is what our team of 5 people tried for 5 years and failed. So those libraries can really make your work go much faster. But the problem is that they are hard to develop, and we need people like you who learn how to write good C++ codes and libraries. And since that will help our work in research, but the problem is that once you know how to write such a library, you're in so much demand that you typically don't stay in science, but you leave, go to a company, make money, enjoy your life. There are more libraries, but I think that's what we'll do next time. So let me stop here for today. Other questions?